Good evening. This is Professor David Koilpillai from IIT Madras regarding the course Introduction to Wireless and Cellular Communications. A warm welcome to all the students who have joined us on the online for this question answer session. Very happy that you have taken time to be with us, and I will be happy to answer any questions that you may have. We have received some questions from students ahead of time, and also an opportunity there for you to post questions even as the session is progressing, and we'll be happy to take up the questions. So let me sort of give a brief snapshot of where we are in the course. We are close to the halfway point. We are in week 5. And this week, you have been looking at concepts such as coherent versus differential detection. In a wireless channel, one of the key challenges is the ability to track the channel. A coherent receiver must have complete knowledge of the frequency and phase information of the channel. So, which means that it has to constantly track the channel, estimate the channel, and track it. That is the challenge of a coherent receiver. On the other hand, a differential detection is a technique that does not require a coherent receiver. You can actually detect the information that is transmitted without the use of a coherent receiver, basically a non-coherent receiver. Subsequent to that, we have started to look at the computation of bit error rate in fading. We have expressions for the probability of error in an AWGN channel. We have shown how to extend it in the context of a fading channel. We have looked at it primarily for relay fading channel. We've also looked at what are some of the other types of fading that we will encounter in a wireless channel, apart from a relay channel where there is no line of sight component. You have a Rician channel where there is a line of sight component, and then there is a varying degrees of the strength of the line of sight component. Now, apart from this, there is also an analytical tool or a model called the Nakagami M fading. And that is what we have introduced, which says that we can characterize both Rayleigh and Rician as special cases of the Nakagami M fading channel. And we have shown what the value of what the parameter M does, and how to understand the severity of the fading channel for the different values of M. One of the tools that is very useful for us in doing the bit error rate analysis is the moment generating function. So for each of the 3 probability density functions, we have shown how we can get expressions for the moment generating function and how that could be used for the calculation of the bit error rate. So that is the scope of what has been covered in week 5, and assignment number 5 is also currently open. Again, if there are any specific doubts or questions, we will be happy to answer. One of the TAs, Anirudh, is also here with me, and together we will be happy to answer any doubts or questions that you may have. With that quick introduction to week 5, let me answer the questions that have already come online on the spreadsheet, and then look at some of the questions that are coming in even as we speak. The first question is from Vijaya Kulkarni, and or a comment was, I want to know more of the basics of OFDM technology. Let me present a slide. I'd like to present a slide, and just give us a minute. We will show you the slide that is on the screen, and we'll explain the OFDM part in a. This is part of the presentation that you would have seen in week 1. So we said that there are different types of multiple access that we can that we encounter. And what we would like to see is the where does OFDM fit in. So if you think of the multiple access as 3 dimensions, frequency, time, and power, and look at the FDMA, frequency division multiple access, we find that the frequency division multiple access assigns each user a specific frequency in which they can transmit with full power all the time. The next type of visualization is that of a time division multiple access channel, where the users are sharing time slots. So basically the sharing happens on the time axis, but when it is your time slot, you can transmit over the entire frequency bandwidth. The third way of multiple access mode is when you can, you're using, all the users are using the same frequency all the time, but they are separated by means of the spreading code that they are using. That is code division multiple access. Now, in this context, we have seen how orthogonality is there in each of the three dimensions. The final one is when we introduce OFDM. And so with this picture in mind, you'll be able to easily visualize what OFDM does. OFDM in many ways is like FDMA. But notice that there are no guard bands in between. So the advantage is that it's a very efficient form of multiple access. The advantages of having narrow channels is there for OFDM. The ability to build wideband channels is also there for OFDM because you can increase the number of these sub-carriers. So for example, you can use 64 sub-carriers, you can extend it to 256 or 2048 sub-carriers. So that is how the latest systems such as the 4G system, which is LTE, the 802.11 Wi-Fi modes, version A and G are all using LTE, the OFDM-based transmission system. So the key to remember is that we are using many narrowband channels, and they are being concatenated and processed using the FFT and the inverse FFT, so that we have very efficient methods of processing these signals. So that is a quick explanation of what OFDM is, and if there are more questions, please feel free to ask. We'll be happy to answer them as well. Now, the second question came from Senthil Kumar. The question, let me read the question. In cellular mobile communications, when a mobile phone is in motion, is there an apparent change in frequency or a actual change in frequency? So let me address that. Let's take a very simple case of a mobile tower and a mobile phone and a transmission happening in this direction. Let us assume that the mobile phone is moving away from the tower, away from the. So what we find is that in this case there will be a Doppler. Doppler will be present. You are moving away from the source, so therefore the Doppler frequency will be negative. In other words, the result. It appears as if the carrier frequency is now lower by the value of the Doppler shift. Now, by the same token, if the mobile phone was moving towards, then in this case, the Doppler would be positive. You will have a positive shift. So in this case, it would be positive. So basically, Doppler is always present when you have motion of the either the transmitter or the receiver, and always it is a physical shift, but the shifts are much smaller than the channel bandwidth. What do I mean by that? So if you look at a GSM signal, the channel bandwidth is 200 Hz. Now if you look at a carrier frequency of 900 megahertz, a carrier frequency of 900 megahertz, you can see that typically for the range of the vehicular speeds that we will have, the Doppler shift, Doppler is of the order of, maximum Doppler will be of the order of 60 hertz or maybe 100 hertz, 60 to 100 hertz. So notice that the order of magnitude of the Doppler shift is much smaller than the band channel bandwidth. The other point to keep in mind is that the signal reaches the mobile not in only one mode, but maybe there is a building here which is acting as a reflector. Maybe there's another building which is also acting as a reflector. So what we find is that the mobile receives signals from multiple sources. Notice each of these have a different orientation with respect to the signal being received. So any motion of the mobile is cause different Dopplers in these different multipath components. So what we ultimately receive is a superposition of these multiple signals which have all got Doppler shift. So it is not just one Doppler shift, but it is a variety of Doppler shifts depending upon the multipath components that are present in the signal. I hope that clarifies the doubt that was raised. And of course, if there are any more questions, we'll be happy to answer them. A couple of other students, Lakshmi Chaya Khandi and Siddhant Avalkond, said that there is no questions. They just sort of indicated that they would be joining the call. There's a question from Balamurugan. The question is, the antenna used in a mobile phone, is it a directional antenna or is it an omnidirectional antenna? Good question. Let me answer it in this fashion. If you looked at the older generation of mobile phones, they actually had an antenna that was visible on the top. Now, these antennas were designed to be omnidirectional antennas. So basically, any direction around the antenna, you would see that the radiation pattern was more or less the same. So this was the omnidirectional antennas. Now, on the other hand, if you have antennas that are inside the phone, and I believe we did look at some antennas of that type. Let me see if we can pull up one such antenna. Not sure. Yes, we can see it here. So notice that there is a printed antenna, and this is inside of the phone. Now, many of these antennas are what you would call a inverted F antenna, and these are inside the phone. So notice that in this particular case, there is an omnidirectional antenna, the one that is outside. This would the antenna that is inside the phone is also designed to have radiation in all directions. In other words, you should not have to do too much of change of orientation for you to get a good signal. However, antennas of this type do not have strictly omnidirectional radiation patterns. They do have some directions in which they have better radiation. And so in some sense, for these external antennas which are called the stub antennas, you could call them closer to an omnidirectional. The inverted F antennas generally radiate in all directions, but do have some directions which are stronger than others. Okay, the next question, this is from Surender Reddy. While traveling, why do you get a disturbance of signals? And may the reason for that? That would be happy to explain. Again, I'm going back to a slide which we covered in the initial class. So if you can please visualize the figure in the bottom right-hand corner. This is way the channel response is for in terms of a spatial distribution. So there are some places where you will see good frequency response, some which will not give a good frequency response. So let me see if I can draw it in a fashion that would be easy to visualize. So let us say that you're moving from point A to point B. Point A to point B. Now, based on the spatial distribution and nulls, we can say that in this particular, there are some locations where the signal is good. So this we can call it as signal strength. And so visualize yourself as a mobile going from point A to point B. Now, notice that there are times when you are going to have, let us say that this is the threshold for a good channel. This is anything above this is good channel. Good channel conditions. Anything below is not so good. Moving from A to B, notice that there will be periods of time when you are below the threshold for good signal reception. Now, if you were not moving and you were only in this particular position, then you would not have a problem because your signal strength would be good. On the other hand, if you were in is bad and you are not moving, that would be a very bad situation because then you would not be able to have communications at all. But the good thing is in mobile communications, we are constantly moving around. So as you move from A to B, you can see that there are some portions where the channel is good, some portion the channel is not so good. We cannot avoid it because these peaks and troughs are there as a spatial distribution. So as I walk from, let us say, from one end of the room to the other end of the room, we will go through these nulls. And typically the spacing between these periods of poor signal quality is of the order of lambda by 2. So typically, if your wavelength, if your carrier frequency is 900 megahertz, this will correspond to a lambda of 1 by 3, 1/3 of a meter, or approximately 33 centimeters, and lambda by 2 will be approximately 16 centimeters. Okay, so if you move by 16 centimeters, then it's likely that your signal may go through a momentarily signal degradation. So this is what makes mobile communications very challenging. And this is what you will see, that as you are moving in any direction, you will find that periodically, at some intervals, you will find that the signal quality degrades and then automatically comes back up. What happened? You moved away from the region of bad signal strength to another location where the signal quality improved. So one important observation to note: if you are a pedestrian, it is more of a challenge because it will take you a longer duration to move out of a position of bad signal quality to a position of good signal quality. So it basically the duration of bad signal will be higher than if you were in a vehicle. So pedestrian versus a vehicular user, but the disadvantage for the vehicular user is the number of these what we call as signal fades will increase. So low mobility users, the duration of the bad signal will be longer because you are it will take you longer time for you to cross from bad signal condition to good signal condition. Vehicular, you will move very fast. But because you're moving fast, you're likely to encounter more of these fades within a given time window. So in a fading channel, poor signal quality is something that we cannot avoid. Momentarily, there will be conditions when the signal quality will degrade. But the challenge is, how do we design for a system where we are able to address these issues? Okay, so those were the questions that had come to us in terms of the now, maybe we can quickly look at the questions in terms of the online chat. So, how do I scroll up to the top? Scroll to the top, and then I can take it. So let me go through in the sequence that that we have received, and this will help us to address the questions raised by the students. First question from Radhika Purandare. The question is, could you elaborate on question 20 of assignment 3? What exactly is to be done and what is the method to solve the question? So assignment 3, question 20 has to do with estimating the path loss exponent. So what you would have to do is take the path loss equation, and then we try to solve for the path loss exponent. Now, what we can do is maybe over the in the discussion forum, we can give you some additional hints once we know till what point you have been able to receive. But I believe we would have discussed something similar in around lecture 5 or lecture 6. So you can take a look at that earlier lectures, and then you will see that we have done some comments on the path loss exponent. However, if there are any difficulties, we'll be happy to give you specific suggestions. So basically, the question 20 is about estimating the path loss exponent. Next question from Manasa Markandeya. How to switch signal between cellular towers? Good question. Let me answer that. So typically, when you have different towers and you are a mobile that is moving in a particular direction, at some point, the other tower, let's call this as tower A, B, and C, you will be probably hearing all three towers, but A is probably the strongest at this point. And as you move from this point to this point, eventually B becomes stronger. So you would then do what is called a handoff and connect to the tower that is tower B. Now, this is what we call as handoff. And this is something that the network will take care of. We do not have to do anything. And the user does not have to intervene and do anything for this. So automatically, the mobile keeps reporting if there are other base stations that are stronger than your own base station. And then eventually the network decides that you have now moved to a position where it is no longer advisable to be connected to tower A, but actually to be shifted over to tower B, and therefore a handoff will occur. So this is a mechanism, what we call as mobility management. This is part of any cellular system, and this is one of the key challenges in a mobile communication system, because you have to manage the mobility of thousands and thousands of users on a real-time basis. And whenever they move from being closer to one tower to another tower, automatically a handover should occur. Otherwise, what will happen is that eventually the quality of, if you did not do a handover and you kept moving away from tower A, eventually the quality will become very poor, and then the call will drop. So we do not want to have dropped calls or minimize the probability of a dropped call, and therefore handoffs are very key for us to maintain good signal quality. Another student has signed on. Hannah is online. Manasa Markandeya, is there is the two towers are connected through wire or wireless? Okay, now the way I would like you to visualize this is in the following manner. Both of these towers are connected to what we would refer to as the core network. A core network has got switches, gateways, and all of the other functionality. It also has the, so basically these towers should be connected to the core network. It's all of these towers have to be connected to the core network. Now it is also it's also a feature that these towers can also be connected to each other. So sometimes, because information may be shared between the towers. Now, in the current generation and fourth generation, this would be based on fiber. this optical fiber. This would also be based on optical fiber. Of course, you could have other connectivity like a E1 or a T1 line, but the way it is evolving, most of our cell phone towers in India do have fiber optic connectivity to their to the towers, and therefore very high speed communication can take place between towers and between the towers and the core network. Okay. Manasa has also asked the question, is there a difference between TDM and TDMA? Very good question. So let me go back to the time or to the figure which explains TDMA. So TDMA is a mechanism by which we create time slots, and these time slots can be dynamically assigned to users. And when one user finishes, for example, blue could be the user assigned to me. Once I finish speaking, then again that same resource can be given to somebody else. So the way to visualize a TDMA system is as follows. TDMA, there are time slots, and these time slots occur at regular intervals. Time slots given to users, but here comes the main difference. They are given to users for a specific duration of, let us say, we call it a call. And once the call is over, it will be reassigned. Third step in a multiple access system, we want to make resources available to all the users. There will be a reassignment of the resources. Now, contrast this with TDM. TDM also has time slots, and very often that is maybe the reason why there's some little bit of a doubt saying, okay, are we talking about the same thing? No, we are not talking about the same thing. But in a TDM system, what we have is multiple users who are assigned. Okay, so multiple users are using the time slots, but it is assigned on a permanent basis. Okay, so basically, this is on not on a dynamic basis like what we do for multiple access. This is maybe you can call it permanent or longer duration. So basically, these time slots are not as dynamically given to users and taken away. They are basically assigned for longer periods of time. So multiple access is a highly dynamic system. Time division multiplexing is primarily a transport mechanism. So this you would focus on the multiple access part. Many users who are trying to get to use the resources. This is a primarily a transport mechanism. I want to go from point A to point B. So I want to connect from point A to point B. There is a cable that is a fiber optic cable that is running. We create a hierarchy. Maybe there are 24 time slots. So time slot number 1, time slot number 24, then time slot number 1, time slot number 24. So basically, the time slot mechanism. This is assigned to 24 different users so that we can carry their data from point A to point B. So it's primarily a transport mechanism as opposed to TDMA, which is a multiple access mechanism. Okay. Let us continue in the list of questions that come. We have answered the question. Manasa has also asked another question. What is the basic difference between wavelength division multiplexing and frequency division multiplexing? Okay, very good question. Again, let me see if we can answer it in the following fashion. Frequency division multiplexing is very similar to FDMA. Different users get different frequencies to operate in. Now, when it comes to wireless channel, we call it FDMA. Now, when we go towards optical, so in the optical domain, that is fiber optical transmission, we find that we have different channels. These are frequencies of transmission which are different. Like FDMA, they're also present, but these correspond to specific wavelengths of optical wavelengths. Optical wavelengths. Okay, so one wavelength will correspond to one frequency. So basically, there's a relationship between the wavelength and the frequency. So in some sense, wavelength division multiplexing says that you are giving users a particular frequency band which is characterized by an optical wavelength. So that is the key. So in wireless, we say, okay, you are giving a channel based on a frequency. So in a sense, wavelength division multiplexing and frequency division multiplexing are talking about a very similar concept. One is in the context, strictly in the context of optical, because there is a, in optical, we talk more in the context of wavelength of the optical signal. In the case of wireless, or in other communication channels, we talk about it in the context of frequency. So I would say that they are analogous and definitely something that can be used interchangeably, but mostly optical will mean that you are using the term wavelength division multiplexing, and in other communication systems, frequency division multiplexing. Okay, Manasa has a question. Can I have a brief discussion on different cellular technologies? Most definitely. Please take a look at the this PowerPoint. Actually, gives a very good summary of what all the different generations of cellular systems are supporting. So basically, all the way from if you go down and look at the for this particular slide, you will see that there is the evolution all the way up to 4G, and then also we have addressed the aspects of 5G also. So yes, please do take a look at the presentation, and if there are any questions whatsoever, please you can send an email directly to me or post it on the forum. We will definitely respond to that. Okay. There's another comment. I want this topic notes. The lecture notes for each of the lectures are uploaded each week along with the videos. The lecture notes are also uploaded. I hope you're able to access it. In case you are not able to access it, or if you have questions on the notes, please do let us know. We will clarify and then help you work with this. Okay, and a couple of more students who are online, and very happy that you have joined, Mohammed Abdul and Nisar Ahmed. Thank you very much for being online. So we have more or less come to the end of the questions that are online. Let me maybe briefly summarize what we have discussed today. A couple of the key questions have been on the aspects of multiple access, frequency division multiple access, time division multiple access, orthogonal frequency division multiple access. We also had a question where we were trying to understand what are the aspects of handoff. How do you go from one channel to the other? Okay, a few more questions have come in. We'll be happy to take a look at it. There is a question. When we have a mobile phone registered in a region, say New Delhi, when I make local calls from my mobile, we have to prefix the local regional code. Could you explain? Very good question. So typically, the digits that you dial for making a phone call have to be recognized by the network. So the first task of a network when you are making a call is for the network to recognize, are you calling another mobile Are you calling another mobile within the same operator or outside of the operator to another operator's network, or are you calling a landline in this case? So the ability of the network to recognize which number you are dialing. So if you were dialing a local number, maybe an 8-digit number, the network can be confused because your mobile today may be in Delhi, is registered in Delhi, but another day you may have temporarily moved to Bangalore, you may be visiting Bangalore. Now, if you dial an 8-digit number, there is an ambiguity. Are you dialing an 8-digit number which is to be in the interpreted as Delhi region or in the Bangalore region? So to avoid this ambiguity, whenever you dial a landline network, you actually have to dial with the area code also, so that there is no confusion and the call will be appropriately routed to the switch in that particular location. So it is important that, and that's the reason why we do that. But for mobile to mobile calls, it automatically recognizes the 10-digit number and then recognizes who the operator is, and then accordingly the calls will be handled. Okay, next question. While traveling, how the mobile recognizes and displays the present location? Very good question. So the way it is done is that if you take let's say you're traveling from Bangalore to Chennai to Delhi on a train, as you go through the different regions, we talked about a handoff. Your mobile will be handed off from one tower to the other, because as the train or a car is moving, you will find that you are now moving from the coverage of one tower to another. Now, each of these towers has got a unique identification code. And with that identification code, you can also know what are the lat-long coordinates of that particular tower. So once you know that you are connected to, let us say, you're passing through Vizag, and you know that you connect to a tower there, and then automatically the display will tell you what is the local area that you are passing through. It's based on the identity of the cell phone tower that you are connecting to. So that is the a simple key. There is, these towers have a registered identification. Once you know the identification of the tower, that's how you're able to track it. Maybe an interesting point. This is how the police also track criminals, because if somebody has made a call before a crime is committed and they are able to trace the phone number of the person who has committed the crime, they can then see which was the tower to which they were connected last, and then they're able to zero in on the geographical area where the person most likely will be found, because that's the tower to which they connected. So more than one application. Maybe rather than the crime application, you can think of it as location-based services. If somebody knows that you are on MG Road in Bangalore, they could actually tell you that there is a Pizza Hut or there is some advertisements for the local. They know where you are. How do they know where you are? Based on the tower to which you are connected. So that's one of the unique features, one of the major advantages of a cell phone cellular technology is that the network can know where you are and use that information accordingly. Okay, good. Let me quickly take a look at some of the other questions. If you can spare some time to discuss one MATLAB simulation of a complete wireless channel in brief. Yes, we will definitely be happy to do that. We are still waiting for MATLAB, the licenses to become available. However, we do have some MATLAB assignments that we will be happy to share with you. But I believe that you are asking for a complete simulation of a wireless channel. Now, that is an assignment that we have not included as part of the course, but we are more than happy to help you design a MATLAB-based experiment where you can have a complete, a transmitter, a fading channel, and a receiver, a complete wireless communication system, and how we can simulate it and look at its performance. So, but please do get in touch with us via email, and then we'll be happy to help you with that. Okay, let me move on. That question was from Harsh Sethi. The next is Mauptika. What is the difference between FDM and MCM? By MCM, I'm assuming you're talking about multi-carrier modulation, and FDM is frequency division multiplexing. As we mentioned, MCM is another name for OFDM. MCM is another name for OFDM. Now, this is a multiple access method. Many users are given these subcarriers for you to communicate. Now, just like TDM was a transport mechanism, FDM is also a transport mechanism. In the earlier years, 20, 30 years ago, the transmission over long distances happened via frequency division multiplexing. So basically, each one was given a particular channel. So that is what was FDM. It's a transport mechanism. Multi-carrier modulation is another name for OFDM. This is a multiple access method. It's also a modulation method that is used in the 4th generation, the LTE systems. Let me move on. Mauptika has one more question. My question is regarding filter banks and transmultiplexers. Why don't we find any literature on the implementation of near perfect reconstruction filter banks using lattice structures? Okay, you must be a student of multi-rate signal processing. You have asked a question regarding the use of filter banks and transmultiplexers. Now, transmultiplexer is a device that occurs in a transport channel, and the role of a transmultiplexer is to convert a signal that has got frequency division multiplexing to time division multiplexing. Okay. And when would you do that? You may do that at the point of switching. You may go from one format to the other so that you can then regroup the channels in order to transport it to the next destination. So transmultiplexers are used primarily in a transport network. Now, when we talk about a cellular system and we talk about the access methods, we are primarily talking about multiple access, not transport. So the notion of having a lot of users who are being frequency division multiplexed, who are being separated out, is not as much present in a wireless channel because it's used primarily for the multiple access methods. We're not trying to convert them from one multiplexing format to the other. You pick up the channel, the base station receives you, and then provides you service. At the end of the call, you release resources back to the network, and then another user comes on board. So the primary role of a transmultiplexer is in the context of transport networks. This transmultiplexers are where you would find the filter banks, as you have rightly pointed out, filter banks, and these would be used primarily to separate the channels and then to combine the channels once more. And these are very much present in the transport networks, but not in the, so we don't see their use in the access networks. Okay, let me move on. Okay, yes, Mr. Sattar has, yes, okay. If there are any questions, Mr. Sattar, you can please post it. Thank you. There's another question that comes. Which technology is best? GSM or CDMA? Can I have a brief comparison of these two methods? Let me answer this question in the following manner. Go back to the multiple access diagram and notice that the GSM belongs to a family of systems which use time division multiple access. And on the other hand, you have CDMA, which is a code division multiple access. Both have very different ways of establishing or or permitting multiple access. In the case of GSM, orthogonality is maintained very, very strictly because each user is given a dedicated time slot, and this time slot is continuous, is orthogonal to all other time slots. So notice that within a particular cell, there cannot be interference because each user is given a dedicated unique time slot. So a TDMA system is within the cell, within one cell, is completely orthogonal. On the other hand, if you take a CDMA system, what is the major advantage? Each user can use all the frequency all the time. So which means that you can transmit with very low power. Notice compared to a TDMA system where the user is transmitting with full power, the user in a CDMA system is transmitting only with low power. Now, how is orthogonality maintained? Is it always guaranteed as in the case of a GSM system? The answer is no. The reason is you do maintain, you design them to be orthogonal when you generate the signals. However, when these signals pass through a multipath channel, this orthogonality structure where yellow and green and red and blue are all distinct layers, that may not be preserved. They could actually start interfering with each other. So one of the differences between a TDMA system and a CDMA system is that there is potential for loss of orthogonality. That is a very key difference. However, then why would people choose CDMA? The key reason is maybe once again, let me see if we have a slide that will explain this. I'll just see if we can capture that. It goes back to the need to do, no, I don't think we have that slide. In GSM systems, we cannot use the same frequency in every cell because they would start interfering with each other. Okay, so basically what you would have to do is something called a frequency planning. So if I use a frequency in this cell, then I have to allow some geographical distance before I can reuse the cell. CDMA, on the other hand, will allow you to use the frequency in every cell. So potentially, there is advantages and disadvantages for both. At the end of the day, depending upon the type of deployment, I would say that the capacities of the TDMA system and a CDMA system per unit bandwidth will be approximately the same. There's nothing inherently different or advantage. There are distinct advantages and differences. But I would say that at the end of the day, I would be very hard pressed to say, well, this technology is better than this. It all boils down to how the network is deployed, how the network is optimized, and how the service is provided. So that is a key aspect, but a very good question. Okay, what are the applications of FDM, TDMA, FDMA, and CDMA? That's a question from Manasa. As I mentioned, FDM and TDM are transport mechanisms. So point A to point B, long distance. For example, there was a question on wavelength division multiplexing. So that would be something that you would use for long haul or long distance communication. So there is the transport mechanism. That is FDM, TDM, wavelength division multiplexing. Now, FDMA, TDMA, CDMA, these are all multiple access. In one cell, how do I allow multiple users to share resources, either time slots or carrier frequencies or the code? That is within a cell. In one geographical area, you are using this multiple access mechanisms so that users can share resources. So that's a fundamental difference between transport and multiple access. So Sattar is asking a question, what is orthogonality? Very, very good question. Let me see if I can quickly explain the aspects of orthogonality. So orthogonality can be most easily visualized in terms of time. So if user A is transmitting on a period of time, let us say from 0 to T1, and then user B is transmitting from T1 to T2. Now notice that the user A will not cause any interference to user B. So we say that these two users are orthogonal to each other. They will not interfere. A can transmit any signal he or she wants at any power level. It will not cause, because the time at which you are transmitting is different. Now, you could also visualize that, let's say A is transmitting on a frequency F1 and B is transmitting on a frequency F2. So this has been given to A, this has been given to B. So again, as long as there is a reasonable separation between the two, they will not cause interference to each other. So that is again a notion of orthogonality. So orthogonality can be explained or visualized as saying users who are orthogonal will not interfere with each other, will not affect each other. So here again, we have the notions of orthogonality. So keep that as a very simple definition. Orthogonality means non-interfering. They don't affect each other. They don't interfere with each other. Okay. Nisar Ahmed, question, sir, suggest me the core areas for. Oh, very good question. Anything in the 4G and 5G area are there are many active research topics in 4G and 5G. Definitely would encourage you to explore. If you'd like to discuss about specific topics, we'll be happy to give some inputs via email as well. Another question from Manasa: how frequency reuse is possible? Let me see if I can draw the use of frequency reuse notion. So there is a cell that is present, another cell, and a third cell. And so let us say I use a channel F1 in this particular cell. I do not use channel F1 in the blue cell or in the green cell, but I reuse it again at a certain distance away. Now, this is what we call as the reuse distance. Reuse distance. This pattern by which we reuse the same channels in other cells is called frequency reuse. So this is something that is part of the cellular system design. And very specifically, there is a task or a step in cellular system design that is called frequency planning. And frequency reuse is usually designed at the time of the design of the cellular system and when you do the step of frequency planning. So again, a very important step, because this more or less tells you how much interference that you will get from other cells who are using the same channels. You do not want these cells to be too close, because then they will cause a lot of interference and therefore degrade the quality of the communications. Okay, let us quickly look at Bautika says that there are a few questions, but I don't see them on the screen. If there is no time or you're not able to send them, but please do make use of transmission via email. Okay, the last one, Shinu Agarwal, what is the difference between noise and interference? Oh, very good question. Excellent question. Okay, so here is a block diagram of a receiver. Typically, what you would find in a receiver is your RX antenna. Typically, you would find that you would pass your signal through a bandpass filter, and then you would have a low noise amplifier. Then you would have the down conversion to baseband, and at this point you come up with the IQ signal representation. Then you do the demodulation. Okay, that's a very simplified diagram of a receiver. Now assume that this is the transmitter. So the transmitted signal picked up by the receive antenna processed in this fashion. So if I have transmitted a QPSK constellation, let us say that one of 4 possible points. Now, because of the receiver electronics noise, what I receive at the receiver will not be exactly what I transmitted, but it will be in the form of noise. Now, that means there is uncertainty because of the presence of electronics noise. Now, if the signal is sufficiently strong, notice that there is still no ambiguity. I can still detect what symbol was transmitted. Okay, that is what we mean by maintaining the adequate signal to noise ratio. Now, when does this become a problem? It becomes a problem when these signals become weak, which means that the noise in comparison has become more. And you can see that at this point, potentially there is ambiguities. You don't know which symbol was transmitted because the noise is starting to dominate. Now, the characteristics of noise. Characteristics of noise. Okay, first one. It is usually an additive noise. That's the thermal characteristic. It is spectrally white. Spectrum is white. That means it is uncorrelated from time instant to time instant. Spectrally white, and the amplitudes are Gaussian. And this is the reason why the noise gets the name AWGN, additive white Gaussian noise. Now, in this setup, where does interference come from? Interference comes from another transmitter which is also transmitting on the same frequency. Maybe he is not transmitting to you, but he is transmitting to somebody else. But this signal is also entering your antenna. This one is also entering into your antenna. So then what happens? We see that interference is the signal of another base station. So yes, it is additive in nature. It is additive in nature, but it is not spectrally white. It looks like the signal that you have transmitted. So if you transmitted a signal that looks like this, this one also is a signal that looks similar. So basically, the spectral characteristics are the same as your own signal. Spectral characteristics similar to the desired signal. And it is not a Gaussian distributed signal. It is a signal that is a modulated signal. So basically, if you are using QPSK in your own desired signal, and there's an interfering signal also using the same. So the signal is a modulated signal. It is another signal very similar to your own desired signal, modulated signal. So with this a simple explanation, I hope you're able to see noise is an impairment, but noise you can handle by amplifying your own signal. On the other hand, interference is a signal which is very similar to yours. Just like your base station is transmitting, another base station may be transmitting the interfering signal. Now, we have to be very careful because we cannot control the power with which the other base station is transmitting. So the presence of interference has to be addressed through the frequency reuse or through sectorization or through some other technique. Otherwise, there will be a problem. Noise always present. Interference, if the system has not been designed well or is being heavily loaded, then you may have the presence of interference also. So that's the difference between the two. If there are more questions, please feel free to answer that. Please feel free to send it across. Do attenuation, is it related to noise and interference? Very much. When you transmit your own signal, you transmit with a certain power level. If the receiver goes further and further away from the transmitter, then the received signal power keeps decreasing. So typically, if this is the received signal power at a distance d, and this is your distance d from the base station, so this is the Tx Rx distance. Okay, as the this distance increases, you will find that your exponentially your signal level will drop. Now, the effect of signal level dropping is that the noise power is remaining the same. So therefore, if your signal is going on decreasing, at some point you will reach that critical level at which you can detect. If you go any further, then you will not be able to detect the signal. So that importance of attenuation, that attenuation comes because of the separation between the transmitter and receiver. Yes, that is an important role. That's part of the design parameters that we would have to worry about. In filter bank multi-carrier as 5-layer for 5G, how is ICI eliminated through PR filter banks? Maybe a quick comment. In 5G, the discussion is still very much on OFDM based transmission. So they have not yet introduced perfect reconstruction filter banks. So therefore, I would not be able to make a comment on this. Maybe if you have a specific proposal that you're thinking that is being discussed, then maybe you can explain the question a little bit more. Okay, let me see if any more questions. Yes, one question from Shinu Agarwal. What research can be done for cognitive radio? Now, cognitive radio is something that we have not addressed specifically, but I believe in the presentation, way at the end, we would have addressed cognitive radio. So cognitive radio today, where are we seeing its use? We are seeing the use of cognitive radio primarily in the TV bands. In the TV bands, in almost all countries around the world, TV channels have been given for terrestrial transmission. But today, terrestrial transmission of TV is not happening. Most of the TV transmissions are happening over satellite or cable, or over the broadband internet. So the terrestrial channels are not being utilized, and so the cognitive radio based transmission schemes are being used in the TV channels. So cognitive radio, in terms of its current usage, it's called white space radio, and there are many interesting applications. But in terms of actual actual products, we're starting to see some cognitive radio based products in the TV band. So that would be an area where you could definitely explore for more work. Okay, Manasa has a question. What are different antennas placed on cell towers? What are their purpose? Very good question. Let me see if I can quickly sketch something for you. Okay, a typical cell phone tower, you should see the following. If it is used by one operator, you would see a triangular structure at the top. On each face of the triangular structure, you will see 3 vertical antennas. So basically, you should see something on each of those triangular. So what is this structure that we are describing? This is a cell phone tower that has got 3 sectors. Each sector is 120 degrees in terms of the angular spread, and the radiation happens in a 120 degrees sector. Okay, so this is typically how the radiation pattern will be. Now the 3 antennas that are on, so basically those are the sector antennas. So there is RX1, one antenna, the RX2, the second antenna, and there is a TX antenna. Okay, so there is 1 transmit, 2 receive, and 2 receive is for diversity. They are for diversity reception. So what you would see on top of any tower would be at least 2 antennas. One will be for transmit, one will be for receive. Most likely you will see a diversity antenna for receive. Okay. Now, apart from this, you are likely to see a small parabolic antenna. This is an indication that they are using microwave for connectivity between the tower and the network. So basically, this is for what we call as backhaul. This is a microwave link, high bandwidth, point-to-point directional link, and that. So this would be the simplest configuration that you would see. But today, because in India the operators are required to share the tower, potentially you could visualize a single tower. One operator's antennas are sitting there, maybe with some spacing. Another operator's antennas could also be there, on multiple levels. Each of these operators could have their own microwave links. Okay, so what you would see is a much more complex structure that is present. But typically, what you would find on top of a tower are the cell phone transmit and receive antennas. You will find most likely, if there's any other antenna, it would be a microwave backhaul antenna that is present on the tower. Okay, Harsh has asked the question. Once we were talking about handoff between UMTS to wireless LAN. In this case, how will the network handle billing and the individual user protocols? Very good question. This is something that's currently being discussed in the standardization between 3GPP, and it could be UMTS, it could be LTE, it could be 5G in the future. Any of these technologies could interwork with the wireless LAN. Okay, so they are talking about the integration of cellular and wireless LAN. Yes, there is a very important mechanism. This is usually a licensed technology, and it is a paid service. This is usually in the unlicensed bands, and invariably it is a free service. Many places it's free. So yes, it becomes a little bit complicated between, how do you integrate something that is a licensed service for which you have to pay, and something that is unlicensed. But again, this is part of the model that is being worked out, where there is a sharing of resources between the cellular and the wireless LAN. And I believe that at least in many cases, the wireless LAN would be deployed by the operator or by an entity that is linked to an operator. So therefore, in some sense, this is not a public free Wi-Fi. It is probably a Wi-Fi that has got some relationship with the operator, and therefore this would be still, you could treat it as one integrated system. But again, the details are currently still being worked out, because one of the key challenges is mobility between these two. How do we hand off between these two? So mobility and handoff are very, very tricky issues, because cellular, you have a lot of cells. You can easily do handoff from one cell to the other. Wi-Fi is mostly within building. There is no notion of mobility as such. So basically, you just have to. So how will you connect? How will you manage? Those are all very key. And how will the handoffs be handled? Again, this is a tricky problem, but currently work is going on in this regard. Okay, let me see if there are any more questions. Okay, we covered all the questions. It is check. Okay. Do you have any course on cognitive radio also? Not yet, but I believe one of the other IITs, probably IIT Kanpur, has. If you could send me an email, I will check and then let you know if a cognitive radio course is available. Maybe not a whole course on cognitive radio, but maybe some aspects of cognitive radio which is covered in one of the courses on wireless communications. Definitely will be able to pass on that information to you. Okay, one more question has come up. Wi-Fi and wireless LAN are the same. Yes, I'm using it sort of interchangeably. One of the most dominant wireless LAN standards, WLAN standards that we have is 802.11. B was the original standard. Now you have A, G, and you've got several more coming in the pipeline. Now, this family of wireless LAN standards are so dominant that, and the original name for the 802.11b was Wi-Fi. And so we sort of use Wi-Fi and wireless LAN interchangeably. Strictly, we should not. There could be other forms of local area networking, but Wi-Fi is today the dominant wireless LAN standard globally. So yes, so that would be the answer is we are using them sort of interchangeably. Basically, it is a connectivity within a short range, maybe up to 50 to 100 meters. That is wireless LAN. That is what we would envision as the scope of the wireless LAN connectivity. Okay, so I believe we had an excellent interaction time. We will be coming, again scheduling these interaction times on a regular basis. Please feel free to send us email or post it on the discussion forum. Let me just indicate my email ID. Okay. I will, or you can note it down. It's davidk@iitm.ac.in. davidk@iitm.ac.in. Please, would be happy to respond to queries. Just identify yourself as an NPTEL course student, so then I know the context in which the question is being raised. And we'll be happy to share more information. I know there were some questions on cognitive radio. There was also a couple of other questions which probably needed a little bit more dialogue. We can definitely have it over the email link. Thank you very much. We'll see you next time.